Okay, so get this. Imagine like a particle accelerator,
Okay.
but not just any accelerator. We're talking a tunnel that stretches for 100 kilometers.
Yeah, 100 kilometers. That's
Yeah.
right. We're talking about the Circular Collider, the FCC.
Huge.
A truly ambitious project
Yeah.
that aims to push the boundaries of, what we know about the universe.
It's mind-blowing just thinking about it.
Yeah.
And from the looks of it, I mean, from the research that we're diving into today, this thing, the FCC, could rewrite physics textbooks.
Absolutely. And it's not just one collider, it's a series of them.
Really?
It's almost like a relay race of physics.
A physics relay race. I like that.
Yeah.
So tell me more about these different colliders. Like, what makes each of them unique?
So we're talking about three main players. The FCC-e, which is a precision powerhouse designed for electron-positron collisions. And then we got the FCC-h, which is a proton smasher, cranking up the energy to levels never seen before. And then the FCC using electrons to unlock the secrets hidden inside protons.
It's like having a physics toolkit, but with different instruments for different investigations.
Exactly.
But with all this talk of colliders and particles and stuff, what's the big payoff?
Yeah.
What can the FCC tell us about the universe that, that we don't already know?
Well, imagine a universe filled with this dark matter, this mysterious substance that we can't see or directly interact with, right?
Right.
The FCC, with its incredible energy and precision, might just be the key to unlocking its secrets.
Oh, wow. So it's like we're going on a treasure hunt. We're searching for clues to the universe's greatest mysteries.
Yeah, and not just dark matter.
Okay.
The FCC could also shed light on the mystery of why there's so much more matter than antimatter in the universe.
Right.
It's a puzzle that's baffled physicists for decades.
Yeah, it seems like the FCC is poised to answer some of the biggest questions we have about the universe.
Absolutely.
Like the kind of questions that keep you up at night.
Oh, yeah. It's about pushing the frontiers of knowledge and potentially uncovering new laws of physics.
Wow.
New particles, even new forces that we never knew existed.
Okay, now you've got me really intrigued. Let's start with this FCC-e.
Okay.
This electron-positron collider that you called a precision powerhouse. What makes this one so special?
It's all about the Z boson, a fundamental particle that plays a crucial role in what we call the weak force. The FCC-e is designed to produce an astounding number of these Z bosons, like trillions upon trillions of them.
Trillions. That's
Wow.
almost impossible to even fathom.
It is, but that's the power of the FCC.
Wow.
With so many Z bosons, we can study their properties with incredible accuracy,
Okay.
potentially uncovering new particles and forces hidden within the quantum realm.
So it's like using a high-powered microscope to examine the subatomic world in crazy detail.
Precisely, and one of the most exciting possibilities is the potential to finally determine how many types of neutrinos exist.
Right, neutrinos, yeah.
These elusive particles have been a source of mystery for years.
I remember reading about those, like they're like these ghostly particles that can pass right through matter.
They are incredibly difficult to detect.
Wow.
And while we know of at least 3 types, there could be more lurking in the shadows.
Really?
The FCC-e could provide that definitive answer.
So the FCC-e is like a neutrino detective
Right.
on the case to unravel the mysteries of these ghostly particles.
Exactly. And it's not just about neutrinos.
Oh.
The FCC will also produce massive amounts of other particles like W bosons, Higgs bosons, and even these top quarks.
Bro, it's like a particle party in there.
It is.
But why is it so important to study these particles in such detail?
Because by measuring their properties with incredible precision, we can test the standard model of particle physics,
Okay.
which is our best current understanding of the fundamental building blocks of the universe.
So it's like putting our current theories to the ultimate test.
Exactly.
Seeing if they hold up under the most extreme conditions.
Exactly.
This is getting really exciting.
Yeah.
But before we get ahead of ourselves, let's talk about the other big player in this physics relay race.
Okay.
The FCC-hh, the one you call the proton smasher.
Yes.
This is where we crank up the energy, literally.
Yes. This is where we're going to smash some protons.
Awesome. Now, when you say recreating the conditions of the early universe, you're not just talking about high energy, are you? What else can we learn by smashing protons together at these incredible speeds?
You're right. It's not just about energy. It's about density, too.
Okay.
Imagine squeezing an incredible amount of energy into a space smaller than an atom.
Yeah.
That's what happens in these proton collisions. And under those extreme conditions, something amazing happens.
Okay, now you got to tell me more.
Yeah.
What happens? What are we going to see?
Remember quarks and gluons,
Yeah.
those fundamental particles we talked about? Well, normally they're trapped inside protons and neutrons bound together by the strong force. But in these super hot, super dense collisions, they break free.
Break free, so they're just floating around on their own.
For a tiny fraction of a second, yes.
Wow.
They form a sort of cosmic soup
Okay.
called quark-gluon plasma, a state of matter that hasn't existed since the universe was just a few microseconds old.
Whoa. We're talking about recreating the primordial soup of creation here. What can this quark-gluon plasma tell us about the early universe?
It can tell us a lot about how the strong force works, which is responsible for holding matter together at its most fundamental level. You see, we can't directly observe quarks and gluons in their normal state, but by studying how they behave in this plasma, we
Right.
can test our theories about the strong force in extreme environments.
So the FCC-hh is like a cosmic pressure cooker,
Exactly.
letting us study the fundamental forces of nature under like extreme heat and pressure.
Exactly. And by understanding how these forces worked in the early universe, we can gain a deeper understanding of how the universe evolved into the complex structures we see today,
Wow.
from galaxies to stars to planets.
This is blowing my mind. So we've got the precision of the FCC-e, the energy of the FCC-hh, and don't forget about the FCC-eh, which you described as kind of a hybrid of the two.
Right.
I'm ready to hear more about this one.
Right.
How does it fit into this grand scheme of things?
The FCC-ee is like looking at the blueprints before building a house.
Okay.
It uses electrons to probe the internal structure of protons with incredible detail, giving us a deeper understanding of the building blocks of matter.
It's like a subatomic X-ray, revealing the hidden architecture of protons.
That's a great analogy.
Yeah.
You see, we know that protons are made up of even smaller particles called quarks and gluons, but we don't fully understand how they're arranged or how they interact to give the proton its properties.
So the FCC will help us like map out the proton's internal landscape, showing us how those quarks and gluons are distributed.
Exactly. It's like creating a 3D map of a proton's interior, revealing the secrets of its structure and how the strong force binds those particles together. This information is crucial for interpreting the results from that FCC-hh.
Okay.
Because when we smash protons together at high energies, it's those internal quarks and gluons that are really colliding.
So the FCC is giving us the context we need to understand the more energetic collisions happening in the FCC-hh.
Precisely imagine trying to understand a complex machine by just smashing it to pieces and looking at the debris.
Yeah.
You wouldn't get very far.
Right.
The FCC is like having the blueprints for that machine,
I see.
giving us a clear picture of how it works before we smash it apart.
It's all starting to come together now. We're
Right.
talking about this multi-pronged approach,
Right.
using different types of collisions and detectors to paint this complete picture of the universe,
Yeah.
from its smallest constituents to its grandest structures.
Exactly.
But with all this talk of colliders and experiments, I'm wondering, like, what are the specific questions we hope the FCC will answer?
One of the biggest ones is the nature of dark matter.
Okay.
That elusive substance that makes up a significant portion of the universe's mass, but doesn't interact with light, making it invisible to our telescopes.
Right. Dark matter. It's like the universe's hidden hand,
Exactly.
shaping galaxies and clusters, but remaining frustratingly out of reach.
Exactly. We know it's there through its gravitational effects, but we don't know what it's made of.
Right.
That's where the FCC comes in. With its unprecedented energy, the FCC-hh could potentially produce dark matter particles directly, finally revealing their true nature.
That would be a game changer. But even if we don't directly create dark matter, there are other ways the FCC can help us understand it right.
Absolutely. Some theories predict that dark matter particles could interact with the Higgs boson,
Right.
that fundamental particle responsible for giving other particles mass.
Okay.
The FCC, with its ability to produce and study Higgs bosons in great detail, could uncover hints of these interactions,
Okay.
even if we can't see the dark matter particles themselves.
So it's like searching for footprints in the sand, even if we can't see the creature that made them.
Exactly. And the more we understand about the Higgs boson, the more likely we are to uncover the secrets of dark matter and its role in the universe.
This is incredibly exciting stuff. But dark matter isn't the only mystery on the FCC's agenda, is it? What about the matter-antimatter imbalance we talked about earlier?
Right.
How can the FCC shed light on that puzzle?
That's a great question. The matter-antimatter imbalance is one of the biggest unsolved mysteries in physics. You see, according to our current understanding of the early universe, matter and antimatter should have been created in equal amounts.
Right.
And when matter and antimatter meet, They annihilate each other in a burst of energy.
So if they were created in equal amounts, shouldn't the universe be empty? So we just wiped each other out.
Exactly. But we're here surrounded by matter, which means something must have tipped the scales in favor of matter over antimatter in the early universe.
Yeah.
And that's where the FCC comes in. One of its main goals is to study this fundamental property of particles called CP violation.
CP violation. That sounds pretty complex.
It is a mouthful, but it basically means that the laws of physics are not perfectly symmetrical when it comes to matter and antimatter. There are subtle differences in how they behave, and these differences could be the key to understanding the matter-antimatter imbalance.
So by studying CP violation, the FCC can help us understand why there's more matter than antimatter in the universe.
Precisely, it's all about looking for those tiny cracks in our understanding of physics, those subtle asymmetries that might seem insignificant but could have had profound consequences for the evolution of the universe.
This is mind-blowing stuff. But before we get too lost in the complexities of CP violation, I want to circle back to something you said earlier. You mentioned that the FCC could help us test the standard model of particle physics.
Yeah.
What exactly does that mean, and why is it so important?
The standard model is our current best description of the fundamental building blocks of matter and the forces that govern their interactions. It's been incredibly successful at explaining a wide range of phenomena, from the behavior of subatomic particles to the structure of atoms.
That's like the periodic table of particle physics.
Exactly.
Giving us a framework for understanding the fundamental constituents of the universe.
Exactly. But like any scientific theory, the standard model isn't perfect. There are some things it can't explain, like the existence of dark matter, the mass of neutrinos, and the matter-antimatter imbalance, just to name a few.
So it's like a map with some blank spots.
Yeah.
Areas that we haven't fully explored yet.
That's a great analogy.
Yeah.
And the FCC is like sending out explorers to map those blank spots to see if there's something beyond the standard model, a deeper theory that can explain the mysteries we haven't been able to solve yet.
Now, that's what I call a grand scientific adventure.
Right.
But with all this talk of pushing the boundaries of knowledge, I have to ask, what are the practical implications of this research? How will the FCC's discoveries impact our everyday lives?
That's a question that always comes up when we talk about fundamental research, and it's an important one.
Right.
While it's difficult to predict specific technological applications at this stage, history has shown us time and time again that fundamental discoveries often lead to unexpected innovations that transform our world.
That's true.
Yeah.
I mean, who could have predicted that studying the behavior of electrons would lead to the invention of computers and smartphones?
Exactly. And the FCC, by pushing the limits of our understanding of the universe, has the potential to spark similar technological revolutions.
So it's not just about satisfying our curiosity. It's about investing in the future.
Absolutely. The technologies that emerge from the FCC's discoveries could revolutionize fields like energy, medicine, and computing, leading to a brighter future for all.
This is incredibly inspiring. I'm starting to see the FCC not just as a scientific endeavor, but as like a testament to human ingenuity.
Yeah.
And our just insatiable thirst for knowledge.
Exactly.
It's like we're setting sail into uncharted waters, with the FCC as our vessel and the promise of groundbreaking discoveries as our compass. But I'm curious, with all this focus on the unknown, is there anything about the FCC that really has you particularly excited?
You know what really fascinates me?
Yeah.
Is the potential for the FCC to give us a glimpse into the very fabric of reality.
Okay.
To help us understand why the universe is the way it is.
Okay, now you're speaking my language. Tell me more about this glimpse into the fabric of reality.
Well, let's talk about the Higgs boson for a moment.
Okay.
This particle, which we've touched on a bit already, is responsible for giving other particles mass, but it's also deeply connected to the stability of the universe itself.
Hold on, the stability of the universe. Are you saying the universe could be unstable?
It's a theoretical possibility. And it all comes down to this thing called the Higgs field, which permeates all of space. You see, the Higgs boson is just an excitation of this field, like a ripple in a pond. And the shape of this field, what we call the Higgs potential, determines whether the universe is stable or not.
Okay, I'm trying to follow along here. So the Higgs field is like this cosmic landscape, and the shape of that landscape determines the fate of the universe.
Exactly. Imagine a valley surrounded by mountains.
Okay.
If the Higgs field is sitting comfortably at the bottom of that valley, the universe is stable.
Okay.
But if it's perched precariously on a mountainside, it could potentially tunnel through to a lower energy state.
Okay.
With catastrophic consequences.
Catastrophic consequences. Now you've got my full attention. What kind of consequences are we talking about here?
Well, if the Higgs field were to tunnel to a lower energy state, the fundamental constants of nature, the very laws of physics as we know them, could change. It would be a cosmic upheaval, potentially reshaping the universe as we know it.
That's both terrifying and awe-inspiring at the same time.
Yeah.
So how does the FCC tie into all of this? How can it tell us if we're, like, on the brink of a cosmic collapse?
The FCC, with its ability to study the Higgs boson in unprecedented detail, can help us map out the shape of that Higgs potential.
Okay.
By measuring the Higgs boson's self-interaction, how it interacts with itself, we can determine whether the Higgs field is sitting in that stable valley or teetering on the edge.
So the FCC is like a cosmic surveyor mapping out the energy landscape of the universe and telling us if we're on solid ground or standing on shaky ground.
That's a great way to put it. It's about understanding the fundamental nature of reality itself, about answering the question of why the universe is the way it is and whether it will always be this way.
This has been an incredible journey into the heart of the FCC and the mysteries it aims to unravel. I feel like we've covered so much ground, from the tiniest particles to the fate of the universe itself.
It's a testament to the scale and ambition of this project. The FCC represents this global effort to push the boundaries of human knowledge and explore the universe at its most fundamental level.
And as we've discussed, those explorations could have really profound implications, not just for our understanding of the cosmos, but for the future of technology and humanity itself.
Absolutely. The FCC is a testament to the power of human curiosity, our drive to explore the unknown, and our belief in the power of scientific discovery to shape a better future.
As we wrap up this deep dive, one question keeps echoing in my mind. The source material repeatedly emphasizes this concept of unknown unknowns.
Right.
Those unexpected discoveries that often overshadow even our wildest predictions. What do you think the FCC will find that will completely change our understanding of the universe?
That's the beauty of explanation, isn't it? It's the thrill of the unknown, the anticipation of encountering something that challenges our assumptions and reshapes our understanding of the world. The FCC, with its unprecedented energy and precision, is sure to uncover phenomena we haven't even begun to imagine. It might reveal new particles, new forces, even new dimensions of space and time.
It's almost as if we're standing at the edge of a new frontier, peering into this cosmic abyss with a sense of wonder and anticipation.
Exactly. And who knows what wonders await us on the other side? Only time will tell, but one thing is for sure. The journey will be filled with groundbreaking discoveries and mind-bending revelations that will forever change our understanding of the universe and our place within it.
This deep dive has been an incredible journey, and I, for one, can't wait to see what the future holds for the FCC and the secrets it will unveil. Thanks for joining us on this exploration into the frontiers of physics and the mysteries of the cosmos.
The pleasure was all mine. The FCC represents the pinnacle of human curiosity and ingenuity, and I have no doubt that its discoveries will inspire generations to come.